in a cast product, and cast product is finally you are rolling to have a roll product. So, the distribution of the large entrapments, they are not uniform. As I have told you, we have to worry about the large entrapments only, not fine inclusions, small inclusions, but these large entrapments, they are not uniformly present in the cast product, and since they are not uniformly present in cast product, they will also not be uniformly present in the roll product. So, let us see where they are present. I have mentioned this earlier, but again I am harping on it because this is very important, because in the non-steady stage of casting normally you find these entrapments. What is the non-steady state? That means at the beginning of a sequence, when you are just beginning a sequence, then you will find reoxidation, possibility of reoxidation is there, because the shrouding is not yet complete. So, some amount of exposure with air will be there in the liquid steel at the beginning of the casting. So, more of reoxidation at that stage. So, at that particular stage we will have more large entrapments due to reoxidation. Then at the end of the sequence there is a possibility of getting tundish slag entrain, unless you take care of it at the end of sequence that you do not allow the tundish slag to come in the mold. You allow some amount of small amount of liquid steel to remain at the end of the casting. So, that at the bottom of the tundish you have some steel also. If you allow that to come in, then along with that some small amount of slag also will come. So, the end of the sequence there is a possibility of tundish slag entrainment. And then at the stage of ladle change, sequence means there will be several heats. So, one ladle means one heat. So, when one ladle is getting emptied, the ladle is replaced, another ladle will come, and the ladle is allowed to team. That means the liquid steel from the ladle will fall in the tundish. So, the slag has to be the slag should not be rather allowed to come in the tundish from the slag, from the ladle. When it is getting emptied towards the end of the heat, the ladle is getting emptied. So, liquid steel is coming out, on top of it is slag. Slag should not be allowed to come from the ladle to the tundish. So, you allow either there should be a slag detection system, it will not allow the slag to come, or you allow some amount of liquid steel to remain in the ladle, so that slag does not get inside. So, you have to be careful about those. So, that means change of heat, there is a possibility of some steel what is that called, slag entrainment. So, possibility of entrapment. Then in bend type of vertical mold, in bend type there is a possibility of inclusions than in vertical mold. I have mentioned it earlier, when you have a vertical mold, the inclusions in mold when they are floating up, there is a possibility of that they will go to the top and get absorbed by the slag. But you have a bend type of mold, then there is a possibility that some amount of inclusions will get stuck at the inner radius portion, and the inner radius area will be relatively less clean. So, some amount of exogenous entrapment will be there. So, this we have to be careful. So, what I am telling is, it is not, distribution is not uniform along the length of the casting, not uniform along the width of the casting also. If you have a vertical mold, then the width is more or less similar in cleanliness, but if you have a bend type of mold, then the inner radius area is relatively, near the inner radius area is relatively unclean, so more defects will be there. Then the suitable design of tundish has to be done, so that these large inclusions they float up and get absorbed by the slag. So, the design of slag is important, so that they can absorb the inclusions. The design of tundish is very important, so the residence time of liquid steel in tundish is relatively high. It does not immediately go into the mold. So, during the high residence time they can float up and get absorbed by the slag. This is very important. So, flow control devices like dam, weir, baffle at suitable location of tundish is important. Refractory property of the tundish is very important, of ladle is very important, so that they do not disintegrate and get entrapped in liquid steel. Then sudden fluctuation of speed or mode level, they can cause entrainment in mold slag. So we know that at what stages there are possibility of large entrapments. That means at what stages of casting there is a possibility of poor cleanliness, and we know these are the locations where we have more defects, because possibility of entrapment of large inclusions are there in those locations. So from the during the casting itself, we know certain areas will have more entrapment. So what do? We keep those cast products separately, because we know intentionally if we want to roll it, those rolled products will have entrapments. So distribution of large entrapments are non-uniform. So when you are getting a defect product in a rolled product, when you are trying to correlate with the origin, if you know that certain stage of casting there was a fluctuation, whether in speed or mode level, we can correlate, yes, this particular area, that means after maybe 1 hour of casting there was a fluctuation for a few seconds. So we know in 1 hour which area of the casting was cast. So we know now that area of the casting after rolling it has gone to that particular location. So we can correlate with that. So this correlation is very important. Then what are the common material defects in casting? This is again very important, because when you are trying to correlate with different parameters, I have mentioned the longitudinal surface crack, there may be longitudinal depression with underneath surface crack. Sometimes we are finding only crack, sometimes we are finding depression, and below the depression, underneath the depression, there will be subsurface cracks. Then there may be transverse depression with surface crack. There may be deep oscillation marks on the surface, as I have told you, and below the deep oscillation marks there may be powder entrapment, there may be crack. So if you have these surface defects on the casting, and if you are rolling it to the final product, then it will be easier to correlate. If you do not have these surface defects, but if you have subsurface defects, then sometimes it is difficult to correlate that where from it is coming. Then I have told you this material defects, they can basically material defects in casting. I am not talking of entrapment, I am talking of material like cracks and depression. They can basically origin from two broad categories of the chemistry of particular grade. That means some grades are depression prone, so you will have more depression, more cracks on the surface, more deep oscillation marks for those grades. So chemistry of that grade, that is a origin, or improper casting parameters. Everything was okay, but the casting parameters was not properly selected. There was a sudden increase in maybe speed, sudden fluctuation, that might create some defect. So this is again important. So what is important is the solidification structure and quality, they are correlated. Specific, as I have mentioned, specific chemistry is important, caster design is important. What is meant by caster design? I have told you the mold, it can be vertical type, it can be a bow type, that means there is a curvature in the mold. So if it is a vertical type, then from entrapment point of view it is relatively better, but it is a bow type, that means there is a possibility of the regions which are near the inner radius, surface, solid surface near the inner radius, there might be some entrapment, because whatever inclusions are floating, they might get entrapped in those areas. But in a vertical mold, they will go straight away vertically and get absorbed at the mold slag surface. So the caster design is important. Again, this bow type or vertical type, because if there is a vertical type, then first you have to give a bending during bending of the strand after it comes out of the mold, and then you have to unbend it, you have to straighten it. That means you are putting some additional strain on the surface of the cast product. It might be of the strain, the magnitude can be it will depend on what is the extent of bending, what is the extent of unbending, and at what rate you are giving this bending, whether it is slow bending, whether it is a fast bending. So, all these parameters might create a lot of strain, mechanical strain. So, that caster design, by caster design I mean that also. Then of course, casting parameters is very important. What is the taper you have used? I have mentioned the taper has to be slightly more for depression grades, because depression grades means mold shrinkage. So, mold shrinkage means mold taper has to be more. That means the distance between the two plates of the mold at the bottom of the mold is slightly less compared to the top of the mold. Top of the mold is solidification has not started. Bottom of the mold means solidification has gone to certain extent, say about 15 millimeters of shell thickness has already formed. So, that means if the 15 millimeter solidification has taken place, that means there will be some shrinkage. So, you have to give some taper, that means at the bottom of the mold the distance between the two plates, broad surface of the plates will be slightly less than what is given at the top, that is called taper. So, casting parameter means taper, casting parameter mold taper, casting parameter means mold taper, casting parameter means what type of powder you are using, what is the solidification temperature of the powder or the slag, what is the other characteristics of the slag, what is the viscosity, it all depends on what is the chemistry of the slag. So, that is also important. Then what is important is how much secondary cooling you will give. It depends on the type of grade which is being cast, what is the intensity of secondary cooling, whether you will go for water cooling or mist cooling, whether you go for what is the gradation of solidification, what is the gradation of secondary cooling. It depends on what is the extent of solidification. So, these are all important parameters, these are casting parameters I am talking about. Then I have talked about to take care of central segregation and central crack formation, you can use mechanical soft reduction. That means you are slightly decreasing the thickness of the cast product in a zone which is near the solidification front. I have mentioned the location of this is very important, intensity of this reduction is also very important. If you use less reduction, it will be of no consequence, no effect. If you use too much of this, that means too much of solid reduction, soft reduction you are doing, mechanical reduction is too high, then there might be crack formation. So, intensity and location of mechanical soft reduction is very important. So, that is the idea, you must have the idea where solidification is ending, where the solidification completion is taking place. You can use it through modeling, you can use it from the calculate what is the end result of the solidification, end stage of solidification. So, you have to have mechanical soft reduction in that area, and the intensity of reduction also is very important. So, now let me give some examples like certain defects, how does it look like on a metallographic observation. Like this one defect, we have found that after we have from the slab it has been rolled to HR product, we find that the crack is extending from the surface and going inside the below the surface. So, we wanted to observe it. First we observe this area, this is the area below the crack, and then we observe the area above the crack and below the surface. What we see is this particular area, there is internal oxidation, there are grain growth in this particular area. What does it mean? As I mentioned earlier, this presence of iron oxide with internal oxidation and there is a grain growth, that means this crack whatever you are seeing now, this must have been, you see it is coming, it is joining to the surface. Originally it might have been subsurface, but during rolling it got exposed to the surface. Because of that there is an internal oxidation, there is a grain coarsening. So, this is important. How it can happen? That means defect was existing near the cast surface. I put it here on or slightly below the cast surface. It may be due to deep oscillation marks, because under that there may be cracks, or there may be cracks also, there may be depression, and under the depression there may be crack. If there is a depression, normally below the depression the grain structure is coarse. I have mentioned you earlier, because the solidification rate, the heat transfer rate becomes slow slightly under the depression. So, that particular area, that means the grains are coarse, that area is relatively weak. So, there might be crack formation also during rolling. So, all these possibilities are there, that means defect existing in the cast surface or cast product itself, either on the surface or slightly below the surface, that has created these cracks, and defect has surfaced during hot deformation. So, that means subsurface transverse cracks were there, or cracks were below longitudinal depression either on the surface or below the surface. So, they have come to the surface during hot deformation. So, normally this type of defects, as I was telling you, you will find near the edges and in grades which are so called, we call peritectic grades, that means the carbon equivalent is around 0.1, or in stainless steel family it is a 304 grade, where the chemistry is near the peritectic start region, around 0.55 nickel equivalent by chromium equivalent. So, what we can do, if we find such type of defects, that means we know why the defect has formed. So, we can do minor adjustment of chemistry to avoid this depression tendency for this type of carbon equivalent 0.1. We may slightly make it lower. If we make it lower, that means delta to gamma transformation will take place after solidification. So, this delta to the strain formation due to delta gamma transformation, depression formation due to delta gamma transformation will not occur, and the overall depression will be less. Or we can, first is this chemistry adjustment, another of course is grade specific casting parameters. We know this is a depression grade, so we know that heat transfer is an issue. So, accordingly we have to select our casting parameters. The characteristics of the casting parameters should be such that the heat transfer is suitable, uniformity of addition of casting powder is important, so that in a localized zone at the periphery of the mold surface there should not be a gap formation, and there should not be a depression formation. So, it should be uniform, so that heat transfer is uniform, that is one requirement for these grades. So, heat transfer control through proper selection of casting powder is very important. Normally for these grades, since these are depression grades, you have slightly more taper compared to sticking grades. Taper maybe you have to give 0.9% or 1% for such grades. For sticking grades it is less, maybe 0.7%, 0.6%, 0.65%. So, that is what I mean by grade specific casting parameters. Based on what is the solidification characteristic, you decide what should be the casting parameter, what should be the casting powder, what should be taper, what should be secondary cooling, intensity of secondary cooling, all these issues you can decide. What should be the mold frequency, oscillation frequency, what should be the amplitude of oscillation. This type of grades, depression grades also have very deep oscillation marks, which is a defect. Oscillation marks will always be there in all grades, but certain grade you have deep oscillation marks. So, what do? You try to reduce the negative strip time I have mentioned earlier. How do you do that? You increase slightly the speed, that is one way. You increase the frequency of oscillation, you decrease the amplitude of oscillation. That means if you have these ideas, if you have this knowledge, and you know that depression grades, you are casting a depression grades, you accordingly decide your casting parameters, so that you have less depression. Again, for such grades the problem will be coarse austenite grains I have mentioned. So, how do you do that? Again, heat transfer control should be proper, so that depression is less. If the depression is less, surface will be good. If the surface of the casting is good, there will be less depressions, hot spot formation is less. So, the grains, austenite grains also will be relatively finer. Now, this is the earlier one was, there was no, if there was a crack, there was no entrapment. So, basically the crack in cast product was the problem. In this, now I will talk about an entrapment. So, entrapment is creating this surface lamination. You see this surface, this is the actual surface of the product, roll product. You see it is sort of tearing, there is some additional surface is getting generated. It is very coarse, you can see it with normal eye itself. So, what do? You take a small piece from here, this is actual sample surface, this is surface lamination. So, then if you just take the surface, you remove that top surface, you will find beneath the surface there are some entrapments, some dark materials. It is nothing to do with the surface, there is nothing to do with the normal product of the matrix. It is, you can make out that it is something different. So, you take that material, yes, cut a small piece, put it under secondary SEM, then in under SEM with secondary electron mode, there is not normal image mode, you will see this defect has been magnified. So, this defect will look like this, and when you see what is present there, you will find some calcium is present, some silicon is present, some sodium is present. That means it is basically combination of calcium oxide, silicon oxide, sodium oxide. There will be some aluminum oxide also, but since sodium is present, that means sodium oxide is present, we can infer that it is basically mold powder has been entrained. So, exogenous entrapment of mold powder. Why mold powder? Because sodium is present. Had there been just calcium, here you see calcium is present, silicon is present, sodium is also present. If you take fluorine analysis, you will find that fluorine is also present, aluminum also will be present. So, you can make out from the exogenous entrapment what is the source. So, mold powder entrapment has caused this formation of this lamination. So, you can know depending on whether it is entrapment, what is the type of entrapment, what is the source of entrapment. If it is a crack, why the crack has formed, like the earlier example I gave, this crack formation is associated with internal oxidation, grain coarsening. So, you know that crack must have been present earlier and it has been linked to the surface during early stage of hot rolling itself. So, that means it was existing, pre-existing in the cast product. So, there must have been some crack or depression in the cast product. So, this analysis, from this way you can know metallographic analysis, and if you have the knowledge of the continuous casting, knowledge of the steel making, steel refining, you know whether it is entrapment or you know whether it is crack, you know which type of grade you are casting, you know what is the type of solidification. So, you can tell what are the possible defects, at what stage they have originated, and accordingly in future if the defect has taken place, okay, in future you can take some remedial measures. Now, let me conclude by observing that systematic investigation on surface defects in roll products, what we have done, we have made some physical observations, we have used a lot of inspection, good inspection facility to find out what stage defect is there, what is the frequency of the defect, what is the size of the defect, shape of the defect, and then we have done some metallographic study. That means we have taken samples from here, from the defect areas, carefully observing what is the defect, how does it look like in normal, with normal eye, under microscope. So, with metallographic study we have found out what were the defects, whether it was crack, whether it is just entrapment. Then we have correlated with the grade, with the steel making and casting parameters. So, using all this, people can develop some reasonable understanding on the genesis of different defects. This is very important. Development of genesis of different defects. So, you require physical observation, that means good inspection, you require some metallographic observation study, you require good correlation with the chemistry and the steel making casting parameters. That means everything is required. Here some knowledge is involved, here some practical ideas are involved. So, this combination of theory and practice will finally give you a lot of concrete information. So, what is the remedy? Suppose you have found that yes, defect is taking place, then there can be two remedies. One is either you can do process improvement. Process improvement involves some cost. So, you must know whether through this improvement, that means you are using some some investment, what will be the extent of improvement. Or if you find that okay, it is the investment is too much, maybe then what you do is you live with the defect, but those defects you divert for low end uses. I have mentioned to you at the very first stage of this course that there will be certain defects, but it depends on what type of applications will tolerate what type of defects. Quality of steel is application specific. The certain quality of steel can be used for different applications. A very stringent application will require very stringent quality. A very low end application will require you may have inferior quality. So, you can divert those particular material for low end applications where quality requirement is not that stringent. So, what is important is that you should know what are the application requirements, for what applications you require what quality parameters, and you should also know how to achieve those quality parameters. By quality parameters I mean residuals, entrapments, control of residuals, control of entrapments, and control of defects in cast product. So, using this knowledge you can get the desirable quality which is required for a particular application. Thank you very much.